So, hello guys, welcome back and welcome back to Cheenta School of Statistics and Data Science, and let's get started on some statistics problem solving. So, our students have told us that they are a bit, they really want to know some more details about least square estimates and um, the problems on it. I don't really know what type of problems have come in past years of these estimates. Very few problems have come in IIT JAM MS. So I will try my best to brush up the theory of least square estimates, and then I will move ahead to the some problems based on it. Okay, that's the goal. So let's get started. Number one, what is least square estimate? Okay, how do we calculate the least square estimate? So all these questions come, in the mind. So least square estimate is nothing but a different form of. So I have introduced. I don't know who have done my statistics classes or CC classes, or people of like non-platinum batch must be knowing this. I've introduced them to this way, but people who have not done my statistics classes, to them I have introduced parametric inference like x1, x2, xn. They follow some f of theta of x, and if this was the idea, then we have understood the following, that we are trying by MLE and MOM are nothing but a ways of an algorithm of trying to find very good estimates of theta. They give really good estimates to theta. Okay, and that's the only purpose. That's the only purpose of this. So least square estimate is another such algorithm to give in certain cases. So in a very special case, it's an algorithm to give a good estimates, So this is something I will be just brushing upon the basics of, what is the goal in data science and machine learning nowadays, so that you can just, I will not go not too much deep into it, but I will just tell you and touch the surface, and you will understand why statistical inference comes into play and why it's really important to understand that. So today I was taking the interview of 4 MSc statistics students, and it was really, a disaster, that some people don't know the basics really well. And I was just taking in as a some data science company told me to take some interviews, so it was really not good. So you are from, they have done BSc from Calcutta University, and they're doing MSc from somewhere, and they did BSc from DU and MSc from somewhere. So the basics are not really good. So you must take this opportunity, what you're learning, even if you don't get into IIT or ISI, doesn't matter, but whatever we are teaching you, that should be something related to your basic very well. Okay, so you must keep it to your mind very well, so that you don't forget it. Whatever you do, not all of you will get into IIT or ISI, but the knowledge will stay. So make it stay in your mind and heart. It will matter in the long run, you will see. Anyways, coming back to the theory. So the whole of so now we are doing a very special case. Okay, so essentially the idea is to give an estimate of the parameters. So least square estimate is nothing but an algorithm to give an estimate of certain parameters in certain case. So this theta will just change, but the algorithm will remain same. Okay, so let's see. And also the least square estimate doesn't need the distribution assumption. So least square estimate doesn't need the distribution assumption. Estimate is an estimation of parameters, is an estimation of certain different parameters. So I will tell you what it is. So what they are trying to do is that, if you see the prediction, what is prediction? Prediction is nothing but you're trying to predict a function. So everything you will do in regression and whatever statistics you will be doing, okay, the predictive modeling. So you will see mostly sometimes it will be vector, but mostly it is this, that you need to predict. So y is equal to some fx plus epsilon. So you need to predict the best function f. You need to predict the f hat from data, from the yi xi pairs. This is the core of predictive modeling. Okay. So all the algorithms are, trying to find out the better f hat in certain scenarios. Okay, I mean, not all the models that you will see, not all the models will be, directed towards a certain scenario. So some different data they get and they try to fit in different models. That's why so many theories and research comes up. So that's the like the core idea. We have y is equal to fx plus epsilon. This is the error part, and from that we need to capture the f hat. Okay, the best possible f hat. Okay, this is the basic idea. Okay, so now the best and the easiest function in the world is nothing but a linear function. So if you take the linear function, y is equal to beta naught x plus beta 1, sorry, y is equal to beta naught plus beta 1 x plus epsilon. If you take this is a linear function, this is the fx part. But the good thing is that this fx is known. Okay, so therefore to find a very good f hat over here, it is same as telling you to find a good beta hat and beta 1 hat. Okay, so when there is no parameters, we do non-parametric statistics. Okay, which is mostly about, you will learn about kernel density smoothing. Like I am just speeding out terms that you might have done your data science projects. I don't know if you have done it or not. So kernel density smoothing, or you will do something like, spline regression, and those are all, not spline regression is not per se, like spline method is another way of non-parametric stuff. Also KNN regression, all this stuff are non-parametric way where they don't know the parametric, the functional form. So, and giving an estimate of f hat is same here as giving an estimate of beta hat and beta 1 hat. Do you understand that, guys? Did you understand this, all of you? Finding an estimate of f hat is equivalent in linear regression. In linear case, it's equivalent to finding beta naught hat and beta 1 hat. Do you understand this, or did you get confused? Okay, what about others? Okay, fine. So therefore, in linear regression, we are actually finding f hat, but since the functional form is known, we are trying to find out beta 1 hat and beta 2 beta naught hat and beta 1 hat. That's the goal. Now, what is given over here? So we are given the following data. Just like you're given, there you were given initial. So there you are given just xi's. Here you're given xi's and yi's. Okay, x1, x2, y1, y2. But understand that xi's are all constant. So it is called endogenous regression. But don't forget about that. Like here, xi's are constant. Okay, and yi's are errors. So it is a yi is equal to fx plus epsilon, or epsilon follows some like this is the regression setup. Now I will tell it to you. So y is now the response variable, is now a functional form of the predictor variables plus certain error. This error follows some distribution we don't know. Okay, error follows some distribution which you don't know with mean 0 and variance sigma square. Okay, which may or may not be known. So this is a basic idea, and also this is a basic idea. Y is a random variable which follows fx plus epsilon, where expectation of epsilon is a random variable. It's a random variable, and this is a constant in some sense. We have to find the f. So therefore y is also a random variable. Okay, therefore y is also a random variable, but x is not a random variable here in this case, not in general. So not in this case it's not a random variable. It can be random variable otherwise in some other cases. Can be random variable in otherwise. Okay, x is constant over here. Like There is no randomness over here. So y is a random variable. So the data we have is xi, x1, comma y1. It's an observed random variable, x2, y2, x3, y3, and it goes on till xn, yn. ठीक है, ठीक है. So if you think about it now, yi expression of y is what? Expression of y is therefore what? Is nothing but fx, right? Since expression of epsilon is 0. So therefore yi is nothing but f of xi, right? Expectation of yi is nothing but f of xi. Do you understand this? So now what will happen? So yi therefore follows certain distribution that you don't know with mean f of xi, right? And variance sigma square. You don't know this. This is not known. Okay, since epsilon distribution is not known, but it follows certain distribution, right? Do you get this part? Yi follows certain distribution like this. Do you get this part or not? Thank you, Momita. Yeah. So why I get this? Why I follows this distribution, right? All of you got this? Sure. Others? So this is the real statistics and application of statistics coming up right now. Okay. All these that you are doing, this is the tools. If you really want to know what is an application of statistics, this is where it begins. Okay, so coming back to this, yi follows certain distribution with mean f of xi and variance sigma square. So let me write that down. So yi follows certain distribution with mean f of xi and sigma square. So this is the setup. Okay, this is the setup. So you have yi is now the data you have are is yi, y1, y2, yn with x1, x2, xn. Okay, so x1, x2 are fixed. So data you have now is this. Okay, the data you have now is this. So what is f of x here? F of x is nothing but beta naught plus beta 1x. So therefore you have yi is equal to certain distribution, follows certain distribution with mean beta naught plus beta 1 xi and sigma square. This is the distribution of yi you have. The question is that then let's say you know this part or maybe you don't know. The question is that how do you get estimate? How do you get a good estimate? That's the only goal, right? To get f hat. That's the goal from this data. How do you get good beta naught and beta 1 estimates? So this is a goal. Okay, this is the goal of the problem. Good. So understand that. So I will just tell something, but okay, did you understand the goal right now, guys? Did you understand what is the goal? See how y1, y2, yn follows. I'll beat like y1 follows. So let me write it down again. So y1 follows beta naught, some distribution with mean beta naught plus beta 1 x1 epsilon square epsilon 1. Y2 follows some same distribution beta naught plus beta 1 plus x2 comma epsilon 2. Sorry, what I'm writing, sigma square. Right, this is continuing. So this is, we have this data till yn. The question is that how will you get a good estimate of beta 1 hat and beta 2 hat? So initially what was the framework? Initially the framework was y1 follows certain distribution, okay, certain distribution or certain f of theta, right, and it continues. There the goal was to find theta hat. Okay, that was probabilistic in nature. How did they do that? They did it by MOM. If you observe that MOM, method of moments, and MLE are the two methods, MOM doesn't require the knowledge of the distribution. MOM just requires the moments, not the distribution. Okay, if you know the distribution, if you know the moments, then it's done. Not the distribution, not the entire distribution. Like the first few moments. But MLE requires the entire distribution. These are certain things that people misses. Okay, that's why I'm just mentioning it to you over and over again. MLE requires a distribution, but MOM doesn't require the distribution of assumption. Okay, this is very important. So, but there here we cannot use MLE right away. We cannot use MLE. Okay, we cannot use MLE. Why? Because we don't know the distribution assumption of yi's, right? We cannot use MLE right away. So we need a different method. Okay, can we use method of moments? Can we use method of moments? So we can try that out, maybe. We can try that out. We can try that out, of course. But there is a problem. Okay, I will tell it to you. So can we use method of moments here? No. Why? Because we don't know the distribution of this. Since we don't know the distribution, just mean and variance will not give rise to. So the variance will be equal to sigma square, right? The sample variance will be equal to sigma square. The sample mean will be equal to this, but we need two variables out there. Okay, we have two variables. We need two equations for beta naught and beta 1. So MOM will also not be a good thing over here. Do you understand? MLE we cannot do because we don't know the distribution assumption. MOM we cannot do it using this because the distribution, the dense, the variance is based on sigma square, not this one. So there will be only one equation for two variables. So that is not possible. So therefore we need some other method. Do you understand, guys? Did you understand this? It's very important. Did you understand this, guys? Any doubts? Thank you, Mansi. Okay. Vendula Orko, Dibangana, Mansi, Faizan, Nikhil, Paulami, Shoikot, Ramit, Sriteja, Shondipon. Okay, fine, good. Okay, so now coming back, so we need some different methods. Okay. So remember, what is the core idea of finding a good estimate? I have told this initially. The core idea of finding a good estimate. What is the core idea? The core idea is that, in some sense, the distance between the actual parameter and the estimated parameter must be as minimum as possible, right? This is the core idea. The distance between, in some sense, the distance between the actual parameter, I mean, it can be the expected distance and the estimated parameter. It must be, we don't, Momita, we don't know whether it follows normal or not. When did I say it follows normal? There is no condition. I told it doesn't follow normal. I have like, did I say that they follows normal? No. So the distance between the actual parameter and the estimate parameter must be as inverse. In some sense, likelihood can be, framed into a distance parameter, but that I have not done. It can be framed in that way, okay? But like that's something we are not doing because that is not really, I just given like that will take some time, and it is not something doable now. We can do it sometime else, or I can make a video on it. So the question is that the idea is that the distance between the actual parameter and the estimate parameter must be as minimum as possible. So the idea is that y is equal to fx plus epsilon is the model, and we are trying to estimate like y is equal to f dash of x, okay, like f hat of x. This is the core idea. What is that f hat? What is that f hat? So now the idea is that we are trying to minimize nothing but a distance between f hat and this. This is what you're trying to minimize, right? We're trying to find an f hat that is very close to this. Okay, that is very close to this. Very good. So now understand this in this case. So we have under the actual, we have y1 is equal to beta naught plus beta 1 x1 plus epsilon 1. Okay, we have other conditions that yi's are IID, like not IID independent, so therefore epsilon i's are also independent, okay? And this continues. This is something that is the actual model, right? We don't know this beta naught hat, so we are trying to model it by what? Like this is the idea. But you will be understanding there will be certain errors also. What are these errors? Let's understand this. This is a true. So y is equal to fx plus small epsilon. Okay. So we are trying to find y hat is equal to f hat of x. That's the idea, the closest possible value. Okay. This is the basic idea. So we are trying to find y hat. So this y hat are these ones. So this y will be this, but we are trying to find the closest possible value of y by approximating this. So this y hat will be this ones. That is the fx hat. Okay. So these are the estimated ones. Like these are the estimated means, sorry, not the estimated one. These are the estimated ones. So understand this. We are trying to understand very carefully. Y1 is equal to beta 1, beta naught plus beta 1 x1 plus epsilon. This is the model. Okay. This is the entire model. Okay. Now we are observing x1. Like x1 is like constant. These are constant. So we are observing y1s, y2s, and yn's. From that, we are trying to find the parameter beta naught and beta 1. How do we do that? We are also observing this. How do we do that? We are going to find beta naught hat and beta 1 hat x1. So whatever we will be getting that will be some y1 hat, right? What is that y1 hat? Y1 is nothing but the approximate value of, like, when you approximate that f by f hat x, you replace that, the value you get That is the y hat. Okay, that is the closest possible value of y. So you may be thinking like, what do you mean by closest possible value of y? You can think in this terms. Okay, so the goal is to find f hat of x. So now if you think that if you put that x, then whatever value you get, what is that? That is y hat. The goal is this. The goal is this, that, so if you think in this manner, f y1 is equal to fx1 plus epsilon1, y2 is equal to fx2 plus epsilon2, the dot yn is equal to f. So this is the parameter. So why did I write like this? I have to write the parameters. So you can also write that as beta naught plus beta 1 x1 plus epsilon 1, beta naught plus beta 1 x2 plus epsilon 2. So we'll be teaching this again, like, after this IIT. So the idea is that we want to find the closest possible value, like from beta naught to the beta hat, right? What is the closest possible value? What is the closest possible value? So for this, we will get what? Let's say we have found out the closest possible value, beta hat, the best possible value. Okay. Then the value this will be giving, this is what I am calling y1 hat. This is approximate, like the closest possible value that we could have got. Like the y1 is the actual value. It's a random variable. Remember, it's a random variable. We are getting a closest possible value of that y1 with respect to y1 hat. Okay, this is the estimated value. Okay, we're getting the closest. We're trying to get the closest possible value of y2 hat. Okay, and this goes on. So we have y1 is equal to beta naught plus beta 1 x plus that error term. So we're trying to get beta naught hat and beta 1 hat. The idea is that we are going to try to get the closest possible value of beta naught hat and beta 1 hat. So that means after putting in that value, we are trying to get, in fact, a closest possible value of y1 in some sense. Okay, we're trying to get the closest possible value of y1. So in some sense, the idea is that, let's see the errors. Okay, let's see the errors. So the errors over here are nothing but, okay, will I rub this? Yeah, let's rub this. The errors over here nothing but y1 minus beta naught, the error, that is the expected error, but this is something random variable. Okay, remember that it's a random variable. Again, these are all random variables. Remember, y1, y2 are all random variables. This is something we have observed, and it goes on. So these are the errors. So we have observed the errors now. Okay, these are random variables. Now we have observed the errors as y1 minus that. These are all random variables. Okay, remember, these are all random variables. We observe them to be this. And it goes on. Okay. So the errors, epsilon 1, epsilon 2 dot epsilon n, these are the errors. Okay, these are random variables in itself. So we have observed them to be this one. So the idea is that we have to minimize the error, right? Because minimizing the error will give the minimum distance between the this one and like the beta naught hats. So therefore we need to minimize this. These are the which we have observed. So therefore that means this vector has to be minimized in some sense. Like all of them will be a minimum. So vector of errors has to be minimum in some sense, and it's equivalent to the fact, has to be less, is equivalent to the fact that the length of the vector has to be minimum. Okay, the length of the vector has to be minimum. Length of the vector, let's call it E vector, which is nothing but summation of EI square has to be minimum. And to minimize it, we will see how to minimize it, but this has to be minimum. Okay, so let me revise that once again. So we have the random variable y is equal to f of x plus epsilon. This is a random variable. Okay. So for y1 we have small x1, for y2 we have small x2. This goes on till yn. Now the question is that how do you find that f? Say f contains some parameter theta, but how do you find that f? Some theta. Here theta is nothing but beta naught and beta 1. The question is how do you find the best theta? The algorithm is the following. Writing in the algorithm, I've told you the meaning of the algorithm. The algorithm is the following, that we observe this y1, y2, the real, like whatever the random variables of observation are, and we subtract that from this. So these are nothing but what? This is nothing but some unknown parameter, right? This is nothing but what? The unknown parameters, like a function of the unknown parameters, g theta. Okay. Like for example, in that case, it's y1 minus beta naught minus beta 1 x1. Okay, this is the unknown parameter. It's a function of beta 1 and beta 1. A y1 and x1 are known. So it's like this. So similarly, you will get g2 theta, some different parameters, g3 theta. These are called residuals in some sense, e1, e2. So it's like it's behaving equivalent to what? It's behaving equivalent. These are realizations of the errors. Because the randomness is coming from the assumption of the errors, right? It's relations of the errors. So we are trying to minimize the error. That's the whole idea. We're trying to minimize the realization of the errors. That's the algorithm. And we get this and we try to minimize this. So therefore we try to minimize the vector e1, e2, en, which is same as minimizing the sum of squares. That is, we are minimizing g1 theta square dot dot gi square. So let's see what will look like. It look like the error, this is called loss. The error, it will look like summation of yi minus beta naught, this is the f1 xi whole square. These are individual ei square, the realized, like the realization of each of the individual errors. And we are trying to minimize it. This loss we are trying to minimize, because they are telling that this is nothing, this is in some sense the distance between the true parameter and the estimated parameter. This is in some sense the distance between the true parameter and estimated parameters. Why? Because the ei, this is nothing but a summation of ei square. Ei is in some sense the distance between true parameter and estimated parameters, right? So to minimize this, so now we need to minimize this with respect to minimize this. The loss is nothing but a function of beta naught and beta 1, right? Now we need to minimize this function because for different beta naught we will get this loss. So we need to minimize f of beta naught and beta 1 with respect to beta naught and beta 1, and therefore we need the calculus over here. So we do double derivative, we do derivative like with respect to both of them, partial derivative, and if you observe we will get 2 will be getting out common always, is equal to 0 when you do del, let's call it L, del beta naught, it respect to comes out this, the minus over here, and there's a minus 2 yi minus beta naught minus beta 1 xi 0. So it's when you do del L del beta naught beta 1. So this is what you get, guys. Did you understand till this point of time? Any doubts? So any issues where you're facing? Mansi, did you ask this question? Did you feel like, what are the questions you have in your mind? Tell me. What are the questions you have on your mind? Did you understand or not? Which part you didn't understand? Tell me. It's clear? For others, what are the issues you're facing, guys? Shaina, Vendrila, Orko, Dibangona, Mansi. This is a new topic. That's why I'm asking you. It's in the IIT syllabus. Okay, thank you, Orko. What about others? It's clear for all of you? Paulami, Romit, Shondipon, Sriteja. Sure? So now we are trying to do this. So now this is like, do I need to do the calculation, Mansi, because it's a very generic calculation that is done in the classes. So when we need to use LS estimate, that's a very good question. When we need to use the least square estimate? So usually least square estimate is used in regression setup. Usually least square estimate is used in the regression setup. That's it. So do you need me to do the estimate and calculation, guys? Do you need me to do that? Please tell me. Then I will be doing that. Tell me, please. Okay. Months you don't need it? So MOM is not feasible when method of moments is not feasible when you don't have the moments information of the population. Example. Okay, there's an example, like like this is an algorithm. Like example means I have to show an R example. Like it's like the math behind this is this. But like, what do you mean by example? Can you please tell me, Mansi, what do you mean by example? I don't know what type of problem JAM gives. I don't know. Like, have you guys seen problems in JAM on this? I really don't know. Usually only in Momita, only in regression setup. Yeah. Also, let me tell you something. Let's say an example. So in the previous case, what was the distribution? What was the form? The form was y1, yi follows certain distribution we don't know, which mean beta naught plus beta 1 xi comma sigma square. So what we did, we took the loss function of, we defined the loss function to be this. This is the least square algorithm, okay? Is in some sense the distance between the norm, okay, or the length of the vector of, let's call this set of sample, this it's like y vector minus, okay, like it's the distance or the length of the error vector. So we write it as summation of yi minus whole square, okay, and we minimize it. This is the core idea. We need to find a loss function and we minimize it, okay. So let's say the usual framework. How does the usual framework, how does the usual framework fit in here? The usual framework is what? Yi follows certain distribution with mu and sigma square. Here the parameters are mu, so beta naught and beta 1. Here the loss function can be defined as what? Just a function of mu as summation of yi minus mu whole square. Right? So then we can minimize it. So we can do this problem. So it can be done in a general case also. Here the means are changing. Here it is not IID, it is independent. And here it is IID, independent and identically distributed. So in this case, it's an algorithm also. It's the same algorithm. Okay, we need to find this mu. Okay. So the question is that how do you define, how do you minimize this? So let's do the minimization problem. So loss is nothing but it's 2 minus 2 summation of yi minus right, simple, is equal to 0. So what's getting out? It's getting out that mu is nothing but y bar. So you see that it gives the same estimate as the MOM estimate, and it's a very good estimate. Do you see how least square method, least square algorithm is extendable to this case in general numbers, not only just in case of regression. See, understand, regression, it's nothing but, in regression, in this setup, it's not identical. The rest is same. It's yi just follows this, okay. Here yi follows this. Everything is same. The idea is that the means are changing over here and the means are not changing over. It's constant. In the general case, it's constant. In other case, the means are changing. Okay. In other case, means are changing. That's it. And you don't know how the means are changing, but the means are changing. So then how do you find a good estimate? That's the question. Do you understand, guys? Did you understand it, guys? This is very important. How least square estimate can be extendable to this case? Now I also told you that how the loss function is defined. Loss function is nothing but the distance, or it's a measure of the sum of square of the errors. Okay, that's it. It's considering all the errors possible and minimizing it. Very good. Okay, so let's move on to the next idea. That so this is only, I think, we will teach you this. No worries. Applications of least square estimator, applications of, okay. So what I will show you something interesting. So we have seen that least square estimate is different. So least square estimate is first discovered by Gauss. Okay, when he was calculating the, you know, the orbital movements, and he was calculating something, the best possible curve fitting, okay, to the orbital movements of the some planets. So the least square estimate, so he was estimating the curve and the parameters of the curve. We were trying to find the parameter, good estimates of parameters. So then he discovered this. So least square estimate is different from MLE, right? We have seen that. This is something I have told you. Why? Because it's very natural. Least square estimate doesn't require distribution assumption. Nothing. And MLE requires distribution assumption. We need to find out the probability, likelihood. But I will show it to you that in a certain case, special case, MLE is equal to least square estimate. So we have assumed that yi follows certain distribution beta naught plus beta 1 xi comma sigma square, right? This, you can just take it as an example problem, Mansi. So if we assume that this is normal distribution, okay, then we will find out the MLE, and then we will find out the least square estimate. We will show that they are equal, like they're always equal. Okay, that's it. So let's go ahead to it. Okay, let's go ahead to it. Just give me a minute. So if we assume the distribution to be normal, then least square estimate is equivalent to the MLE estimate. So let's say yi follows normal sum f of xi comma sigma square, independent. So let's find out, the first step is what? Find out the likelihood joint distribution. Like, let's call it G, okay? So therefore, remember least square estimate was what? Least square estimate is nothing but L is nothing but summation of f of xi minus yi whole square. And since f of xi contains the parameters, this is a function of the parameters. It's called f theta. It's a function of the parameters. And you minimize it. So let's call it g theta. Okay, and here the joint density will be nothing but f of y curl, nothing but product of I from 1 to n, 1 by root 2 pi sigma, ठीक है, and exponential minus half. So what is the mean over here? Sorry, yi minus g theta of xi by sigma whole square. This is the joint distribution. And if you do the product, it will be 1 by, so it will be root 2 pi whole to the power minus n by 2 into sigma whole to the power minus n into exponential minus half summation of I from 1 to n yi minus g theta of xi by sigma whole square, right? Right? Now this is nothing but, what are the parameters? It's nothing but the function of, certain function of, let's say h of the parameter theta, like whatever parameter we are trying to find out. Let's say here theta is nothing but beta 1 comma beta 2, beta 1 out comma beta 1, but in general. Rather it's a function of, yeah, it's h of theta, right? Now we want to minimize this, right? Let's take the log likelihood. So let's take a log likelihood. So if you take the log likelihood, what it will turn out to be? The sigma is constant. If you take log likelihood, there is some constant plus, sorry, minus what? Half times summation I from 1 to n yi minus g theta xi whole square, right? This 2 sigma square over here. So therefore we need to maximize this, right? The log likelihood with respect to theta. So it's same as minimizing, because it's minus over here, minimizing what? This summation, and this is a constant. It's same as minimizing summation of I from 1 to n yi minus g theta of xi whole square, which is nothing but the least square estimate. So in normal, if you assume the errors to be normally distributed, always for any regression framework, for any regression, we have done it for the general case, for any regression framework, the least square estimate is same as the normal estimate. And at that time, Gauss only knew normal distribution. So out of that, he did the MLE, and because MLE was already done by Fisher at that time, he did the MLE, or was it done by Fisher? Maybe I'm just confusing, but he did the MLE by the Fisherian method, and he discovered the least square method because both are equivalent, and then least square method became another way in general. Did you understand the proof, guys? Did you understand that how the least square method in general case is equivalent to the fact of MLE in the normal distribution with normal distribution assumption? Did you understand this? Thank you, Ansi. This is something very important. So we have 3 different estimators. We have seen the relationship between MLE and normal. So okay, so thank you, China. All of you understood it? Orko, Dibbangana, Nikhil, Mansi, Paulami, Romit, China, Vendila, Shundipon, Ucho, Triteja. So these things will not come in ISI or IIT, but these things are really important for your basics. You should be respecting that. This is of course a problem for a practice problem. Bishal, you didn't get me? Okay, so do you want to know the connection between that actually method of moments and MLE are in some sense the same thing. That's why many of the results are coming so close. Do you want to know the relationship between method of moments and MLE? But this is not in the syllabus, so it's my asking. Like, do you want to know now? So they have a common SU, like they have a common like they're actually the same thing in some sense. Do you want to know that today? Because if you don't know it today, I will not tell you now. So it's a very fundamental no. This is an algebraic same way. I mean, you saw the same wave there, algebraically same, right? It is least square estimate and the MLE. In some sense, the MLE and the method of moments are algebraically same. Something is just changing, nothing more. Okay, are you guys interested or not? Just let me know because exams are in like very close. So do you want to know it today? Okay, sure. Very good. So this was a question I had in my mind for a long, long time. For a very long time, okay? And I didn't get an answer in anywhere. Last year, while I was teaching you guys, not you, but your seniors, sorry, I somehow discovered this. And this is very interesting. Let's see. I hope I can wrap it up in 4 boards, but let's see. So let's first see that what is method of moments. Very carefully. What is done in method of moments? Method of moments are, so it is for those who know method of moments, okay? That's it. So in method of moments, what we do? We connect the mu1 is equal to the sample um, sample mean. Wait, the sample moment 1. How do I represent it? Let's say it's a function of the x curl h1x. Mu2 is nothing but h2x, which contain the parameters also. And let's say mu k, till mu k we are doing it. This contains the parameters. So when we equate that, this is the first moment, second moment, then it's expectation of x, it's expectation of x square, it's expectation of x to the power k, same thing. So when we do this, we get an estimate of the theta curl, we get an estimate theta curl hat, like theta hat. Okay, this is a curl, like the many parameters, we get an estimate of that. This is essentially what method of moments is all about, right? Now, let's see MLE. MLE, what is done? ML में what we do is the following. We take likelihood, which is product of the f of xi's. Let's say x1 x2 xn follows f theta. Okay, product of fi's, and with a log likelihood, or we try to find the maximum. Let's take log likelihood, like summation of log of f of x theta I, right? And what do? We maximize it, right? We maximize it, right? So my question is to you, to find the connection between the MLE and the method moments, we need to pose the method of moments as a maximization or minimization of some loss function, something like this, something summation of something. So I'm giving you 2 minutes to think about it. So how we can pose this as a maximization or minimization problem? So I will give you some, like, it's a very good, out of box thinking. It can help you. So I'm giving you 2 minutes to think about it. That how this method of moments. The idea is that MLE is nothing but a maximization minimization problem. Maximization problem. So how method of moments can be transformed into a maximization and minimization problem. That's my question to you. Okay? So I'm giving you 2 minutes to think about it, and I will finish my food. In the meantime, I will get back to you. Okay? So think about it, guys. It's very important. This is the only relationship. Similarly, also you understand that in least square estimate, it is also summation of something, some function which you're trying to minimize. Here also is some function you're trying to maximize. So minus of that function you're trying to minimize. Okay. So think about it. What is that? Think about it, guys. So I'm giving you 2 minutes to think about it. Okay. So it's a break. You can take it as a break. So my food is complete, and any ideas did you get, guys? Any ideas did you get? Yes, no, maybe. Okay, so let's look into this. Let's revisit MOM. So what is MOM? It's nothing but the sample moment, right? What is the sample moment? It's 1 by n summation of xi to the power k is equal to mu k, right? We're doing it like first we're doing it for 1, right? Then we are doing it for n, a 2, and it goes on. How many? How much? Till the k parameters. Let's say k parameters are there. This is the equation, right? Let's now go to MLE. K parameters. So what we do? We have seen that we do log likelihood. Let's say log likelihood is what? It's, observe that it's nothing but summation of log of f of xi, right? This is log likelihood. What we do now? We minimize it. How do we minimize it? And how many times? We do k derivatives. Since there are k parameters, we do what? Let's call it small l. So we do what? We do k derivatives. So we do del l, del theta 1. Okay, k derivatives are there. So what we do? Let's see. We do del L del theta 1, which is same as the theta, the del, this derivative will be going inside. It's same as summation of del L del theta 1 log of f of xi, which is a function of theta, of course, right? Which is a function of theta, of course. Then we do it for del L del theta k, which is a function of theta, of course, is equal to 0. Similarly, we get k parameter, k equations here. You see this, the k equations here, right? Here also k equations, here also k equations. So if we just observe the k equations, here it is nothing but 1 by n summation of xi to the power k minus mu k is equal to 0. In case of MOM, it is this. In case of MLE, it is summation of del L del theta k f of x curl, right? Sorry, I have done something wrong. Xi force given theta. So if you just delete this part, just take it for one parameter, or just you just take this part, it's inside that, called theta curl. So all the equations are of this format, right? Now do you see the similarity? It's 1 by, so if you just add 1 by n over here, it doesn't matter, it's equal to 0 only. It's same. So therefore, if you see, it's of the format, both of them are the format 1 by n summation sum h of what? Xi comma theta is equal to 0. Do you see this, guys? Both of them are the similar format, right? Do you see this? Observe this. If you did you understand this? Yes or no? So therefore, MOM and MLE is nothing but K equations like this. It's nothing but K equations are like this. Estimates. Did you understand this? In that case, in this case, h of xi comma theta is nothing but xi to the power k minus mu k. It's like mu k, it will be like here. And here it's nothing but del del. Did you understand the similarity? So this is a similarity between MOM and MLE. Okay? This is a similarity between MOM and MLE. Did you understand, all of you? Shana, Mansi, Anvila, Orko, Dibangana, Nikhil, Shondipon, Ucho, Sriteja. Very good. So this is the relationship. Now the question is that what is so special about this H? If you observe, the something special about this H is the following. Here, in one case, H is nothing but xi to the power k minus mu k. In the next case, xi is of the form del del theta f of xi given this. Right? So there's a log over here. If you observe, this equation is nothing but saying that the sample of h of xi are, so it's nothing but, if you know it, expectation of xi to the power k minus mu k, this is equal to 0. And if you know the score function expectation, I have told you this is a u while explained to the Kramer or Rohr bound. If you have done it, I don't know if you have done it or not. I think you have done it. This is also equal to 0. It's called score function. So both of them are 0. So this is very special. So it's like we are finding a score function where both of them are 0, and we are equating 1 by n summation of h of xi of theta is equal to 0 of that. This is the basic idea, guys. The relationship between method of moments and MLE. Okay. So I'll just end with a small example. In case of normal, so what are the true h of MOM? What was the h of MOM? It was nothing but x1 whole to the power k minus mu k. and h of mle is nothing but, just give me a minute. Del theta log of f of xi given theta. So if you observe that for normal, let's say normal mu comma 1, in this case, what is this? This is h of MOMS, you know that. It's xi minus mu, right? In this case, what was del? In this case, h of MLE is nothing but, it's del mu of log of that. So if you observe, if you take the log of that, it's coming up to be minus half xi minus some xi minus mu whole square. Now if you did derivative, you will get, it's nothing but minus xi minus mu I, which is equal to 0. Therefore, both of them are leading to the same estimate because the h are same. If you do this, if you will see like that, equal to 0, will lead to this. So if you, so this is the basic idea. This is a relationship between MOM and MLE. Okay. And similarly here also in LSE, LSE the h is nothing but summation of xi minus f of, sorry, yi minus f of xi whole square. This is it over here. So they're all related by a single idea, that's 1 by n of h of xi comma theta, that's equal to 0. We minimize it. So in this case you will not find out to be that because there are two different equations, because there are multiple parameters, but essentially that's a single way of looking into this. At least a different relationship between MOM and MLE. Did you understand, all of you? Did you understand the relationship, guys? I hope you enjoyed that. I hope you learned something new. And this is something you should be learning, okay? This is something you should be learning. And this is something very, very important. And of course, this is not told in ISI at least. And yeah, so that's it. So that is it. And that is to you. And thank you, guys. And I hope you enjoyed this. And any other questions, guys? Okay, great. Okay, so thank you guys, and I will see you in the next class. Bye bye.